Hello everyone and welcome to the tutorial number 11. In today's tutorial I will be briefly be trying to cover the different methods of pressure and velocity coupling. So let's begin. Okay. So till now we have only dealt with the general scalar transport equation, which is just some general scalar transport, general scalar. We were only considering some arbitrary scalar, and we were doing our all our computations based on that. But now we if you look at the fluid flow problems, we'll see that these scalars are nothing but P can be one for the continuity equation, P is U vector for momentum equation, momentum conservation, P is equal to E for energy, and accordingly the S phi and gamma will also change, right? So in this way we can reformulate our general scalar transport equation into different conservation equation forms, right? Okay, so now let's look at the the two-dimensional Navier-Stokes equation. Okay, so and we'll only consider the steady one, right? So steady two-dimensional XY momentum conservation equation and the continuity equation. Okay, so the X momentum, it will be dou by dou X rho UU plus dou by dou Y rho UV minus of dou P by dou X plus dou by dou X mu dou U by dou X plus dou by dou Y mu dou U by dou Y, right? And also let's also include the source term. Okay, let it be. And Y momentum equation, if you write, it will be of the similar form, dou by dou X rho UV plus dou by dou Y rho VV minus dou P by dou Y plus dou by dou X mu. This is the viscous part. Okay, now if you look closely, okay, let me write the continuity equation as well. So unlike the general scalar transport equation that we were dealing with from the beginning of the course, we can see a difference. The difference is that these equations are very highly nonlinear. By that I mean that this in this equation, this u are the unknown, right? U's are the unknowns. We are solving for the u, which also contains the v velocity, right? And this v velocity is coming from solving the y momentum equation, right? So to solve one equation, you need to solve the other as well, right? So this is a highly nonlinear and coupled coupled equation. And what about this pressure term? Pressure term is also an unknown, right? In a flow field, if we have an incompressible flow, if you remember, for incompressible flow, there is no equation for pressure, right? But for compressible flows, we can have the PV equal to MRT, this relation, right? This relation we can invoke, and we get the temperature, we get the density also. This is nothing but the density, right? If we so P is equal to rho RT, is mass by volume. If we get the density and the temperature, we can calculate the pressure using the ideal gas law, right? But for incompressible flow, this is not the case, and this poses a serious problem. And also in the Navier-Stokes equation, if you see, there is a non-linearity coming from the convection term. So here, if you see this part, this has a u square term, right? And also uv, and also v square and uv. So these are all non-linear terms, right? These are all non-linear terms, and these non-linearities causes some problems that we will address it in the that we will see how to address. And also these three equations are very much coupled, because every velocity component is appearing in every momentum equation. So u velocity is appearing in u momentum, x momentum and y momentum both, and v velocity is appearing in the y momentum and x momentum both of the equations, right? And this issue needs to be resolved, and it appears that the momentum it appears in but and also the pressure term is also there, right? So what to do with the pressure term, because we only have equation for x and y, and continuity equation does not actually tell us anything. This is not a transport equation of some quantity. So how do we deal with the pressure term? Okay, so so for example, if the pressure gradient is known, the way to obtain the discretized equation is very similar to what we have done in for the GST equation. For example, the GST, I mean that general scalar transport equation, whatever we had done in those convection diffusion, steady unsteady convection diffusion equations. This is the solution methodology will be similar to what we have done in case of a general scalar transport equation, if we have the pressure gradients known, right? So, but in a general purpose flow, while computing the flow field, we also require the pressure field as well, right? This is also a part of the solution. So the gradient of pressure is not known beforehand, right? but as I told you, if the flow was compressible, we could invoke the ideal gas law and get the pressure from density or temperature or any other two thermodynamic properties, right? So these problems with the non-linearities and the pressure velocity coupling is very elegantly solved by something called the simple algorithm, called SIMPLE, which stands for semi implicit SIM method for pressure linked equations, right? So it is sort of a semi-implicit form. So you might be familiar with the term implicit and explicit, right? So explicit and implicit, these terms we encountered when we were dealing with unsteady problems, right? So in unsteady problems, when the unknown is written as a function of, so if for example u at a t plus delta t is written as a function of u of t only, this sort of tells us that is an explicit form, right? Explicit time stepping. While when we have t plus delta t, that is the unknown is also a function of t plus delta t, then it was something called implicit, right? This gave us a set of algebra equations which were easy to solve, and it gave us a system of linear equations, right? So it was a bit handful to solve using those iterative methods or direct methods or something like that, right? So this simple technique is a sort of a semi-implicit. So it is sort of a not totally implicit, but it has the flavor of both implicit and explicit methods, right? So you will get to know it once if you have followed the lectures, or else I'll just briefly go over the algorithm, right? Okay. Now let's go through the concept of staggering or staggered grid. So what does it mean? So if the velocities and the pressures are both defined at the nodes of a control volume, then some anomalous behavior might show up, right? So let me draw a 2D computational domain. So these are the boundaries, right? The black lines are boundaries, and these are the points that we are interested in. Okay. So if we store the pressure and the velocities, what did we do previously? We stored all the velocities here, right? So if this is P, this is capital E, this is capital S, we stored our values here. So U capital P or phi capital P or whatever quantity. Now if we do that, then what will happen is that you will sometimes get unphysical results. And by unphysical results, what do I mean? For example, let's take a particular computational grid. Let me just remove all these things. Okay, so let this be point P. Okay, and okay, let me just write down all the points. Okay, so for example, we want to get the gradient of pressure in the x direction, right? So dou p dou x at point P, at point P. So how do we get that? And let's just name the boundaries as well. This is small w and small e. So these value can be easily found out using this relation, right? So we can take p small e minus p small w by delta x. Let's say this distance is delta x, and we have the pressure gradient like this. But we do not have the pressure stored in the phase centers, right? So what do? We invoke the linear profile assumption, and the linear profile assumption tells us that the value of p small w can be taken as the average of these 2 points. So what it means? It means that p small w can be written as p small p per p capital W, p capital P plus p capital W by 2. It's just an average. And similarly, p small e, we can write it as p capital E plus p capital P by 2, right? This is the average of these two quantities. Now if we substitute these values in the gradient equation, we'll see it comes out to be PE is nothing but P plus so P capital E plus P capital P minus P capital P minus P capital W. This will get cut, and 2 delta x, right? These two. So what it comes out to be? It comes out to be P capital E minus P capital W by 2 delta x. This is the gradient in terms of the values that we actually know. Because why? Because we are storing by convention till now we were storing the values of the dependent variables at the cell centers and not the cell spaces. That's why we took the average and took an average of the neighboring cell center values to obtain the phase center values. So what will happen in this case? In this case, if say for example the value of the pressure is here say 1 bar, or just write 1, right? It's 1, and here it is say 10, and here it is again 1. Okay, so what will the pressure gradient be? The pressure gradient term here will be P capital E minus P capital W by 2 delta x, right? Which is nothing but P capital E is 1, P capital W is 1 by 2 delta x. It comes out to be 0. But that is not the case, right? Because there is a pressure gradient between these 2 points and pressure gradient between these 2 points, right? These will drive the flow. So whenever you have pressure gradients, you will have flow from higher. So if this the gradient is high here, the flow will move from P to W, and if the gradient is negative gradient is this side, then the flow will go from P to capital E, right? But in this assumption, with this linear profile assumption and storing the storing the variable values at the cell centers, gave us an erroneous result, right? This is called checkerboarding pattern. For example, let me just draw it. It will. So if these values are same, every alternate say every alternate values are same, this will lead to a uniform pressure gradient, which is not the case, not actually the case, right? So why does this happen? This happens because the gradient of pressure at point P does not feature the pressure at point P, right? You can see that, right? So the gradient of pressure at point P has values of only its neighbors, but not where is the pressure at point P, right? We don't have it. There is no information about what is the pressure at point P. So this type of methods gives us this checkerboarding pattern. So this is the checkerboarding pattern. If you see, this is why it's named in such a way. Okay. Now yes. Yes. Does not feature the pressure at point P. Okay. This is okay. Let me. Okay. So what does it mean? So if you see the relation that we got for the gradient of pressure at point P, it only has the values of P capital E and P capital W, right? But it does not have the pressure at point P. Because of that there is no information about what is happening at P, and we are computing the gradient at point P, but we are not at all aware of what the pressure value is at point P. This kind of discrepancies cause these checkerboarding patterns. Okay. Thank you. And same you can check it out for the y direction. For example, let me just briefly write it down. So dou p dou y at point P will be nothing but what? P at n minus P at small s, that is the phases, by delta x, and P n will be nothing but P capital N plus P capital P, and Ps will be nothing but P capital S plus P capital P by 2 delta x. This and this goes, so P capital N minus P capital S by 2 delta x. Similar thing as what we saw in the for the x direction gradient, right? Just excuse me for 1 minute. Okay, so now what can be done? So now the scalar variables, so it is clear that if the velocities are velocities at the defined at the scalar grid points, the influence of pressure is not felt properly, right? As you have seen in the discretized momentum equation, we have the gradient of P term. This term does not show up correctly if we store all the values at all the values of pressure and velocities at the cell centers. So this idea came about that we evaluate the variables like pressure, density and temperature at the nodes, at the cell centers, but calculate the velocities at the staggered grid or at the faces. So what does it mean? Let me just draw a small schematic. So this is our familiar grid. This point P, point W, capital E, north and south, right? So what is the technique telling us? It tells us that uh, we evaluate scalar variables like density and pressure and temperature at the cell centers. This is the cell, these are the cell centers, right? We evaluate all these scalar variables at the cell centers, and the velocity components, okay, and the velocity components will be computed at the faces, or what is called the staggered grid. This is the original grid, and there will be another grid which is called the staggered grid. So staggered grid. So how can we okay, so now we will see how to construct the staggered grid. So for each of the velocity component there will be one staggered grid. So for v velocity we will have one staggered grid, for u velocity we will have one staggered grid, and for w velocity we will have another staggered grid. So the total number of grids that we need in this approach is n plus 1, where n is the number of dimensions. So if it is a one dimensional problem, we will need two grids, one staggered grid for computing the velocity components, and another for computing and storing our scalar variables. If it's a two dimensional problem, we will require two staggered grids for u velocity and v velocity, and one the original grid for computing the scalar variables. So what is a staggered grid, right? So this is the u velocity, right? Assuming it is a uniform orthogonal Cartesian structured mesh, right? So what we will do is we will draw a control volume around this velocity component. Okay, what have we done? So we have just staggered the grid in the x direction. So we just shifted the grid from in the x direction, and this will be the another grid now, right? Let me just draw it in solid line only. So this is the cell for which in which we compute the x velocity. And what are its neighbors? Its neighbors are these cells, right? So this cell neighbor is this one, this one, this one, and this one, right? And what about the y component? So y component will have velocity in this one, y velocity, and right. So we will again stagger the grid in the y direction now, and these will be its neighbors. Okay, so now you understand what the staggering of the grid means, right? So what we have done is that we store and calculate the x momentum value in the actual grid's faces, which is the cell centers for the staggered grid. Okay, let me just write it down. Velocity components in the staggered grid cell centers, which is nothing but the face centers of the original mesh, right? Any issue understanding this problem? If so, please let me know, because it will be very important if you don't have clarity in this part. Okay, so what we have done is that we have just stated that to avoid the checkerboarding pattern that we observed while obtaining the discretized momentum equation, we saw that a staggering is a checkerboard pattern is happening, which is quite unphysical. It gives a zero gradient even with non-uniform pressure field distribution. So to tackle that, what we did is that we decided that all the pressure and scalar variables will be stored in the cell centers, while the velocity components will be computed and stored in the face centers or in the cell centers of the staggered grid. Okay, so what implications does it have for us right now? So now, if we solve for if we solve for this point, we want to get the value of u at this point. So we will solve the x momentum equation and the y momentum equation. So what do we have? We have dou p by dou x, and in this case it's quite easy, right? Because the pressure is already stored in the capital P and capital E part, right? So we have this capital P capital E minus P capital P by del x u, right? Let's just write it as del x u. This is the grid spacing for the x staggered grid, right? Anyway, if we have assumed a structured uniform orthogonal and Cartesian mesh, it is same as del x, right? So now we see that the checkerboarding pattern will not affect, means even if we have a non-uniform pressure distribution. For example, say what was happening initially was so computing the dou p by dou x, we saw that there was connection of W and E, but no connection was there from P, right? So these two were disconnected from each other. But now when we compute the pressure gradient dou p by dou x at this point, we see that these are all connected, this P and E are connected, right? There is no other values in between them which can affect the physicality of the problem, right? So if you see that just by modifying where and which variable to store, we have eliminated the checkerboarding problem that was happening before. Okay, any question till now? Everyone understood? Okay, so let me just give you a demonstration of how this kind of checkerboarding or this kind of staggered grids come into picture while solving the momentum equation. Okay, so as you all must be familiar with, we will have a form like AP not PP, APUP is summation of A and B U and B minus that pressure gradient term dou P dou X plus delta V will also be there because it is integration over the control volume plus some source, right? Okay, now this might be a little bit intimidating, but please try to follow. I will try to make it as simple as possible. There will be a lot of indices, so just keep in mind of what all indices is being used where. How to do that? Okay, let this be the grid. So in this representation, I will only be drawing the U control volume, right? The U control volume I will draw, and so this will be the staggered grid. Okay. Okay. So let this be point P, and let's draw the original grid lines also. So the original grid lines is just staggered by delta x by 2, okay, in the x direction. So what will be the convention that we will follow? So we will follow that the cell centers, the non staggered grid points, that is which will be denoted by a solid dot, right? Let me just remove this solid dot, it will be confusing otherwise. So what are the cell centers? What were the cell centers here? So it is nothing but this was the original grid point cell center, right?
So the dotted line represents the boundaries of the original grid point. Okay. So these are the grid point cell centers, and these are the faces. And the faces we will represent using cross symbols. Okay. Faces or the staggered grid cell centers, using indices capital I plus minus 1, capital I plus minus 2, all these things, capital J plus minus 1, capital J plus minus 2, and all these things, right? And the staggered mesh cell centers will represent it as x, and the indices will be small i plus minus 1, small I plus minus 2, small j plus minus 1, small j plus minus 2, all these things. Okay. So what, let's just name this as capital I, capital J. Okay. This will be what? This will be capital I plus 1, capital J. So I is for the x increment. This will be capital I minus 1, capital J, like this, right? And what will be, these are the staggered grid point cell centers, right? And in the staggered mesh cell centers, if you notice carefully, the J's will not change, right? So it will only have the capital J's, but only the small other than the capital I, we will only use the small I, and the capital J will stay capital J because it is at the same vertical location. The small j's we will encounter when we see the y momentum equation and see the control volume for the v velocity. Okay, so what will be the notation, what will be the index of this point P? It will be small I, capital J, right? And this will be what? It will be small I plus 1, capital J. This will be small I minus 1, capital J, and similarly like this. So now that we are concentrated in this point P, what are its neighbors? Yes. No. So small j, what will be? Small j will be when we have something in so these all these points are at the same vertical height, right? If you see, so since it is in the same vertical height, we are not bothered about the j. So when we do the staggered grid for the y momentum equation, then the small j will come out. So small j will be somewhere here. You are understanding? No. Okay, so let me explain again. I think my diagram is really bad. So if it is capital I, this will be capital I plus 1, capital I plus 2, this is capital I minus 1, right? And we said that the levels in between these, which we have staggered, this will be small I. This will be small I plus 1, this is small I minus 1, and so on, right? And what will happen with the j? So if we see j, this is capital J, this is capital J plus 1, capital J plus 2, and the levels in between will have small j, right? Small j plus 1, all these things. But here if you see, all of these points are in the same vertical level, right? You understanding, right? So if this is capital J, and if you just extend it here, this point will be what? Capital I minus 1 capital J, right? This point will be small I minus 1 capital J. This point will be small I capital J. This one will be small I plus 1 capital J, right? And what will be the small I capital I? Small I and small j? It will be somewhere in between, right? Yes, yes. In here it will be, in this part. Okay, we will not encounter the small j in this x momentum discretization part, but you will encounter it later in the when we see how to deal with the y momentum equation. Okay, when we stagger the grid in the y direction. Okay, so now that we have this, we are concentrated in this point P. So this is the cell we are concentrated in, right? And what are its neighbors? Its neighbors is this one, this one, this one, and this one, right? These are its neighbors. Let's write down the indices also. So this is small I capital J. This will be small I capital J plus 1, right? Because this is one level above. This is small I capital J minus 1. This is already known, small I minus 1 capital J, small I plus 1 capital J. Okay, these are the four neighbors of the point small I capital J. Now if we look at the discretized equation, we will have a form like, let me just take the whole diagram below. For point P, right? And what is the index? Small I capital J. So what will be our equation looking like, the discrete equation? It will be A small I capital J U small I capital J is summation of the neighboring points A and B U and B minus, so what will be the pressure gradient here? It will be dou P dou X, right? So we will have dou P by dou X. So dou P dou X we can write it as what? P capital I capital J, this one, minus P capital I minus 1 capital J by delta X, right? So we will write P capital I capital J minus P capital I minus 1 capital J by delta X times delta V, this is the volume, plus the source term. Okay, and what will be its neighbors? NB will be small I capital J plus 1, small I capital J minus 1, then small I plus 1 capital J and small I minus 1 capital J. Okay, so these are the four neighbors. I think someone is unmuted. Anand, can you just mute yourself? There is some yeah, no problem, no problem. Some kind of disturbances is coming. Okay, so we can again finally write the equation as like this: a small I capital J plus u small I capital J is nothing but summation of a and b u and b plus p capital I. Okay, okay, okay. The negative sign I have taken it inside. Capital I minus 1 capital J minus P capital I capital J times some A small I J. We'll write it like this. A is nothing but this volume delta V divided by del X, right? Okay, so now that we have this thing, you might be wondering where is the V, where is the V velocity, where does it, where is it going? So it all comes inside the A and B, right? So in the A and B, we'll have, so for the in the A terms, A and B, we'll have the F and the D terms. What are the F and D? F is that convective flux, and D is the diffusive flux, as we have done in the and also sir has also taught in the lectures. These are the terms that arise because of discretization of the convection diffusion problem. So there will be something called FW, right? So what is FW? FW is the convective flux coming from the left hand side. What is this? This is nothing but rho u w. Okay. But do you see the problem here? What problem we are facing? The problem we are facing is that what is the index here? The index is capital I minus 1 capital J, right? Just 1 minute. Sorry for the interruption. Okay. Okay, so now if you look at this part, yes. Yes, A is there, but we are considering a uniform mesh, right? So the A term will anyway we are not regarding here right now. Anyway, A is there. If you want, you can keep it. I just wrote it so that it looks clean and simple. Okay. It's just for simplicity purpose. Anyway, A will be there. You can always take a unit area. Okay, so what is the west face here? Okay, I think I'll have to draw again. It's becoming. This is capital P, right? And let's write down the indices as well. This is small I capital J, small I minus 1 capital J, small I plus 1 capital J. Okay, and oh, I think I have messed up again. It will be cross, and this will be what? This is capital I, capital J. This is capital I minus 1, capital J, and so on. So in this case, where we are considering the point P, which is the cell center for the x direction staggered grid, we see that the west face is this one, right? So if you need the flux from this part, what we can do, that we can just take an average of the fluxes at these 2 points. Okay, we'll just take a arithmetic average of these 2 points, because we have the u values here, right? Because we do not have the u values in this part, because we are only storing it in the staggered grid cell centers. We do not have the values in the original grid cell center. So what we can write? We can write it something like this: f small I capital J plus f small I minus 1 capital J by 2. Okay, and what will be f small I capital J? It will be rho at small I capital J times u of small I capital J plus rho small I minus 1 capital J times u small I minus 1 capital J. But if you remember, what did we decide? We decided that the scalar variables will be stored in the centers, right? It will be stored here instead of the staggered cell centers. So now we again have to do another arithmetic average and get the values of yes. Rho I comma j, yeah. Okay, so I have, these are, yes, so these quantities is already available, right? Yes, this is all capital J, yeah, all capital J. I think I mistakenly wrote it. Yeah, but this rho small I capital J and rho small I minus capital J, we don't know these values, right? Because we are only storing it in these points, right? This is the face of the staggered grid, right? This is the face of staggered grid, but also this is also the cell center for no original grid. This is the cell center for u velocity. No. P is any point that we are concentrated in. Okay, P can be anything. P is just to denote the cell center that currently we are concentrating in. Okay. So this is so. Yes. So the original grid is actually this red part. Okay, and this is the staggered grid. Forget about the solid and dotted. The blue line is the staggered grid, and the red line one is the original grid. Okay, just give me 1 minute. I'll try to explain again. Okay, so let this be the original cell. Okay, let me draw a fresh. This is the original mesh. Okay, and these are the cell centers. What is happening? These are the cell centers. Okay, and we said that we will represent them with capital letters, small I plus 1 capital J. This is small I capital J minus 1 and small I plus 1 J minus 1 capital. This is all capital, right? Now what have we done is that we do the staggering in the x direction. Okay, now the staggered grid is something like this. I am not drawing the other grid points because or else it will become very confusing. Okay, let me okay, I'll do one thing. I can draw it like this. And this is the staggered grid cell center. Okay, so now you see and what will be this one, where is it, yeah, this one will be small I capital J, this will be small I plus 1 capital J, this will be small I capital J minus 1, this will be small I plus 1 capital J minus 1. Okay, now the cell center of the staggered grid becomes the face center of the original grid. Okay, is it clear now? Okay, thank you. Yeah, it's a bit difficult to understand. It's better to have a good pictorial representation, or else it will be really difficult for you to grasp it. I will recommend you to do it by yourself, draw a mesh and do the sort of derivation that I am doing right now. Okay, so now P, do not confuse it with the actual cell center. Okay, it's, I just wrote it P because we are concentrating on this point right now. So what is this? This is the cell center of the staggered grid and the face center of the original grid, right? This is the face center, this is the cell center of the original grid, right? And these are the faces of the original grid. Now if we want to, this is small I capital J, this small I capital J, we want the values at this point. We do not have the density at small I capital J, but we have the densities at small at capital I minus 1 delta J and capital I capital I plus 1 capital J and capital I capital J. So what we can do is that we can take an average of it, but these values we know, these U small I capital J, U small I minus 1 capital J, we know. It's actually not correct to say we know, we store the values there, so it's available, we do not know. Okay, so this rho small I capital J, which is nothing but rho small I capital J, we can write it as an average of these 2 points, right? Which is nothing but rho capital I capital J plus rho capital I minus 1 capital J by 2 and times ui small I capital J, and plus what will be this term, I minus 1 capital J. This is I minus 1 capital J, right? So this will be the average of these 2 points. This is what? This is I minus 2 capital J, I minus 1 capital J. Yeah. This will be what? Rho I minus 1 capital J plus rho I minus 2 capital J by 2 times U small I minus 1 capital J. Okay. And in this way we can compute all the other F quantities, and also the diffusion quantities all quite similar, except for the south and the north points. I think it will be quite quite easy if you just follow these steps, and you can also get, for example, let's see about this point, for point number okay. So what is the D? So F and D were there, no? The diffusion flux was nothing but gamma times delta x, right? And also A is there, so we'll just ignore the A for now for simplicity. So here what will be, so for example the south phase is there. In the south phase what will be the gamma? So gamma here it will be nothing but capital okay, I think let me just give me 1 minute. I'll rewrite these indices to make it consistent. Don't worry, these are also correct. I just want it to be, yes. I plus 1 is not there, I minus 1 actually. This is capital I capital J, this is capital I minus 1 capital J. Okay, I actually I think it's a mistake in my part only. So we want this small I capital J, right? This small I capital J. So what all values we need? We need these two values, and we'll take the average. This is capital I minus 1 capital J and capital I capital J. Okay. Okay. Now say if you for the south phase, what is the, this is the south phase, right? So in the south phase, if you want the gamma value, so how can we get the gamma value? We do not know the gamma value here. We only know the gamma value at these 4 points, right? For example, if I plus 1 okay, just give me 30 more seconds. I'll just redo the indices. It will make our life simpler. Okay, so this is I small I capital J small I. Okay, this small I capital J, this is capital I capital J, this is small I plus 1 capital J, right? And this is capital I minus 1 capital J. This is again what small I capital J minus 1. This is capital I capital J minus 1. This is small I plus 1 capital J minus 1, and so on. And this is our point P. Okay, this is the point P that we are Not necessarily. Not necessarily, Deepraj. So we can take anything that I just wanted to be consistent with what I have written here, right? I just wanted to be consistent with this way. You can take whatever floats your boat. Not a big issue. But the only thing that you have to keep in mind is that you have to be consistent all the way. So if you start by numbering your grid points in one way, and in between solving the problem or developing the discretized equation you change the convention, then the whole thing goes to waste. So there is no hard and fast rule on how to what should be the convention, but whatever the convention you have chosen in the beginning, you have to stick to that and be consistent. That is the only criteria. So here this is the south phase, right? So this is the south phase, and the gamma, if we need, so what is the gamma here? So the gamma we will need at this point. Delta x is already known, but gamma at this point, how will we know? But we said that all the scalar variables like gamma, rho, temperature and pressure, we will store at these points, right? So now, rather than taking an average of 2 points, we will take an average of 4 points. Okay, you understand? So now we will take an average of gamma capital I minus 1 capital J plus gamma capital I capital J plus gamma what is this? This will be capital I minus 1 capital J minus 1 plus gamma capital I capital J minus 1, okay, divided by 4. So our D will then become, ds will then become 4 this divided by 4 delta x, okay. So this is the, okay, so it will not be delta x actually, for south phase it will be delta y, right? So this is the way that you will compute the different f and d terms, right? So I think till now it is quite clear. So you have these your governing equations are done. Then we saw how the staggering helps in avoiding the checkerboard pattern. Then we said that we will use a staggered grid for storing and solving the velocity components, and the normal grid, the original grid, for storing the scalar variables, which are nothing but rho, p, t, and the gammas and all other scalar variables. Then we finally arrive at this AP Phi or AP UP equal to summation a n b u n b and the gradient terms along with the gradient terms, and this then we saw that once we have this form we can easily solve it, right? It's quite easy how to solve it, but how to reach at how to get the a and b values, because a and b's will contain f and d, that is the convective fluxes and the as well as the diffusive fluxes. So in this part we saw that how the convective and the diffusive fluxes are being computed, and so yeah, I think up to this everyone is clear. Okay, and similarly you can do it for the y momentum equation also. It will be easy once you have done it for the x momentum equation. You can simply do it for the y momentum equation. Now comes the main important part. Now we will start with the simple algorithm. It is a very elegant solution of the problem, that is that we do not have a equation, a transport equation for the pressure. So it was devised by two scientists. One of them was Indian called Suhas Patankar. He has a book also out, CFD. You can look at it. Very small book. It might be useful for you. Okay. So it is a monumental algorithm that has been that is still being used extensively in the CFD community, called the simple algorithm, developed by Patankar and Spalding. Okay, just give me 2 minutes, I'll come back. now let's go back to the simple algorithm. So let me just write the discretized equation in a simpler form. APUP summation of neighboring points A and B, U and B plus P. Just 1 minute, an important call is coming. हेलो, हाँ भाई, नमस्ते, कैसा है? ठीक हूँ, घर गया था। घर से आया, अभी कल ही आया। क्या कर रहे हो अभी? अच्छा, अभी ठीक है, मेरे को आधा घंटा लगेगा, आधा घंटा बाद आता हूँ। एक क्लास ले रहा हूँ अभी, वो NPTEL का। हाँ हाँ, ठीक है ठीक है। हाँ, हम्म, ठीक है, आ रहा हूँ। हाँ, sorry for the interruption. Okay, where is the pen? Yeah. So what is the P? P is Pi minus 1 plus Pi. Okay. Let's write Pi minus Pi plus 1. Okay. Times sum A plus, okay, ignore the source term. Now what they suggested is that first you take a guess value for all the quantities U and P both. So U and P, which is denoted as U star and P star. Okay. And say this is the actual value, we can write it as the U star. The actual value is a sum of the guess value and some correction term, which the correction term we will compute using the simple algorithm. Okay, just keep that in mind, that first we take a guess value, then we do some kind of operations, and we then arrive at the there has been a power cut, so sorry for the interruption. So is the screen visible and am I audible? Okay, thank you. Okay, yeah, so keep it in mind that first we will take a guess value, and then we will do some operations, and then we will arrive at the correction term, and we will add it with the guess term, and we then get the actual value. Okay, so this is just to this part I just wrote without any indices to give you a holistic picture. Okay, now going back to the actual discretized equation, we will write A small I capital J, U star small I capital J, summation of A and B U star and B plus P star capital I minus 1 J capital J minus P star capital I capital J A small I capital J plus some B small I capital J. Okay. Now since we have these values, what we can write is that we can subtract it with the actual equation, which is nothing but A small I capital J I'm really sorry for the inconvenience. There is some power cut issue going on here. Okay, so what is the original equation? I am just writing the original equation here. This is not star. Okay, A small I capital J plus B small I capital J. So let this be equation 1, equation 2. So what we will do is that we will subtract equation 1 from equation 2. So what does it mean? It means U minus U star. What will it give us? U prime, right? So we will have A small I capital J plus U I capital J minus U star small I capital J is equal to A and B U N B minus U N B star plus P capital I minus 1 capital J minus P capital I minus 1 capital J star minus P capital I capital J minus P capital I capital J star times A small I capital J plus B small I capital J. Okay, so we just subtracted equation 1 from equation 2, and what will it give us? It will give us, this will turn out to be U I small I capital J prime, that is the correction term. This will give us U N B prime. This will be P I minus capital I minus 1 capital J prime. This will be P capital I capital J prime, and yeah, rest is all the same. So what do we have left? We have A small I capital J times U small I capital J star equal to summation of a and b u n b prime plus p I minus 1 capital J prime minus p capital I capital J prime a small I capital J plus b small I capital J. Okay. Now we have another equation in terms of the correction terms. Okay. And at this point a approximation is introduced, right? An approximation which says that this term can be neglected. Yes, 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 right, 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 absolutely, yes, yes, thank you for pointing it out. Yeah, this term will get cancelled out. Okay. And this assumption, the one assumption we will introduce here, that this whole term will be omitted, but this does not have any significant effect, right? This omission of this term is the main approximation of the simple algorithm. And why doesn't it matter much? It does not matter much because this is only the correction term, right? This is only the equation for the correction term. So what implications it actually has? It has, the implication that it has is that eventually however much correction we do, eventually if we go on iterating, through a iterative process, and we get subsequent correction terms, our final value will always tend to the original actual value only, right? Because the correction term we are introducing to correct the guess values, right? And the guess value is corrected at each of the iterations, and eventually it will reach the actual value since it is an iterative method. So this approximation does not actually hampers our solution procedure. So what can we write finally? We can write it as, we can write that a I small I capital J u I small I capital J star is nothing but p capital I minus 1 capital J prime minus p capital I capital J prime a I capital J, and we will just divide it by a I capital J. So u I capital J is nothing but d I capital J. This is a new term that we have introduced. This is the dij. Okay. Now when we solve for this this equation u prime ij, we can then get the value of u small I capital J from the guess value, right? Now that we have this value, we can just substitute it in this part and we will get the original value. But do you see the problem here? The problem here is we do not have a have the values of these pressure correction terms, right? So now comes another important step that simple algorithm does. The algorithm does not do it, but in the derivation of the algorithm does, is that we convert the continuity equation into a pressure correction equation. Okay, what does it mean? So the governing equation for the fluid flow has the continuity equation and the x, y and z momentum equation, right? So we have how many equations? 4 equations. We have 4 equations and how many unknowns? U, V, W and P, right? Right? So we have 4 unknowns and 4 equations. This seems to be a very good position to solve our system of equation. But the issue is the continuity equation is not equation of a particular, not a transport equation of transport, sort of a transport equation. It's sort of a like a what to say. The continuity equation is sort of a enforces the conservativeness in the fluid flow. It does not give us any information about pressure. Okay, so it does not give us any information about the pressure field. Okay, so we cannot consider it as a one of the equations that we can solve to get the 4 unknowns. So what do? We convert this continuity equation into a pressure correction equation, and from that pressure correction equation we obtain the pressure correction terms and we use it to obtain the velocity correction terms, and then we substitute the correction term in the u is equal to u star plus u prime and get the actual value. Okay, now let's see how it is done. So what is the continuity equation? Dou by dou x rho u plus dou by dou y rho v is equal to 0. This is the steady mass conservation equation. Okay, and what does the discretized form look like? Rho u a small I plus 1 capital J minus rho u a small I capital J plus rho v a capital I small j plus 1 minus rho v a capital I and small j. Okay, now you might be confused why is it like this, right? If you look closely, the indices notations has changed. This is because we solve the continuity equation where we solve the continuity equation in the original cell centers, right? We solve it the original cell centers, which is this is capital I capital J. This is what? This is this will be small I capital J. This will be small I plus 1 capital J. Similarly, this one, what it will be? It will be capital I small j, sorry, small j plus 1. This will be capital I small j. Okay, this part is clear, right? So what it will be? So if you see, this is nothing but this term minus this term. This is the net flux in the x direction, and again this term minus this term. This is the net flux in the y direction. So this is the continuity equation. Okay, it's simple, right? Now let's bring this equation down. This will be what? Okay, for row and A we have the values at I small I plus 1j, but for U we do not have, right? Small I plus 1 capital J. Yeah, we have all of them. Okay, okay, let's write. So row small I plus 1 capital J, we have all these values, right? You see, U also at these points we have, because this is the staggered grid cell center. So we have the values of U that we need. So what do we have? Then A small I plus 1 capital J, then U small I plus 1 capital J, right? But what can we write about this? We can write it as U star I plus 1 capital J plus D I plus 1 capital J P capital I capital J prime minus P prime small I plus 1 sorry, not small I, it will be capital I, capital I plus 1 capital J. Okay, this is nothing but U is equal to U star plus U prime, right? And this is the U prime. Clear? Up to this it's clear, right? I hope so. So we can write it down clearly. So it will be U star I plus 1 capital J plus D I plus 1 capital J P prime capital I capital J minus P prime capital I plus 1 capital J. Okay, this is for the which phase? This is for the east phase. Now we'll do for the west phase, north phase, south phase, and all the other phases. Let me just write them down. This will be rho small I capital J. This was the phase that we were looking at, right? This will be a negative sign here, not a positive sign. Okay, plus rho capital I small j plus 1 A capital I small j plus 1, and V will be what? V will be V capital I small j plus 1 star plus D capital I small j plus 1. What will be the pressure terms? This is the north phase, so pressure will be capital I capital J plus 1, yeah, P prime capital I capital J minus P prime capital I capital J plus 1, and minus rho I what will be? It will be small j, A capital I small j, then again V star capital I small j plus D capital I small j, then P what the P will be? P will be capital I capital J minus capital capital I, capital I capital J minus 1, capital I capital J minus 1 minus P prime capital I. Yes. This is for the north face. Okay, so north face is this one, right? Capital I small j plus 1. where capital J, okay, this one, right? So in this part, in this part, this is pressure at capital I, capital J, and here the pressure will be at capital I, capital J plus 1, right? And to get the pressure gradient, we will have to subtract these two terms, right? Because we store the pressure values at the cell centers only, at the original cell centers, right? Yeah, because of that. Okay, and these also will be capital, all capital I, capital J. Okay, so this is a sanity check that you can do, that all the pressure terms and the gamma terms and the these will have the capital I's and capital J's both. Okay. Okay, so now that we have this, we want to do some manipulation. So this is the continuity equation, and this all goes to 0, right? So now if we do some simple manipulations, what kind of manipulations? So we will take this term P capital I, capital J, this is P capital I, capital J, P capital I, capital J, and again P capital I, capital J. Okay, and we will take all the coefficients of this. So P prime capital I, capital J times rho dA is not, dA is not small d, this is, d is coming from this d. Okay, so this will be what? This will be small I plus 1 capital J, then plus rho dA small I capital J plus rho dA capital I small j plus 1, and plus rho dA capital I small j. Okay, you get where these are coming from. This is coming from this part, this is coming from this is coming from this, and this one from the first line. Sorry. Okay, so we now have P prime capital I, capital J, and we can also club all the other terms also together. So here we have, say, P I plus 1J, capital I plus 1J. This is this will also have these coefficients. So let me just write them down. You can just verify it yourself once. So this is rho dA small I plus 1 capital J P prime capital I plus 1 capital J plus rho dA small I capital J P prime capital I minus 1 capital J plus rho dA capital I small j plus 1 P prime capital I capital J plus 1 plus rho dA capital I small j times P prime capital I capital J minus 1. Okay, these are done, and what all is left? These U star and V star terms, right? Let's write them down as well. So we'll have what? Rho U star A small I capital J minus rho U star A small I plus 1 capital J plus rho V star A capital I small j minus rho V star A capital I small j plus 1. Okay, now if you see that it is sort of a similar form to the discretized general scalar transport equation that we had, right? So if it is for example phi ij, and these are the neighboring grid points, so we can write the above equation something like this. We can write a capital I capital J p prime capital I capital J is a capital I plus 1 capital J p prime I plus 1 capital J plus all the other terms, right? All the other terms will be what? I minus 1 capital J, then capital I J and J plus 1, and capital I J minus 1. Okay, these all terms. And another term will be there, something called B prime capital I capital J. And what will be this B term B? B prime term B? The B prime term is nothing but that rho u star A capital small I capital J minus rho u star A small I plus 1 capital J and all these things. Okay. So now that we have this thing, we can get another form, right? So A P prime capital I capital J, or let's write capital P prime P is equal to summation of A and B, P and B, P prime and B plus B. Okay, and this B is nothing but this, and these are all known, right? Because these are all the star terms, these are all the guess values. Okay, now we have another equation. So you see from some simple assumptions we came to a new equation that was not present before, which is the transport equation, or not the transport equation actually, we cannot say it as a transport equation, but a equation for the pressure correction term. So now that we have this equation for the pressure correction term, now we can do what? We can solve it using any kind of method that we want, explicit direct method or iterative method, whatever is feasible to us. Then once that is done, we have obtained the pressure correction, and then when we have the pressure correction term, we can then apply the pressure correction term and get the value of the velocity correction, and finally when we have the velocity correction, then we can correct the velocity. Okay, so let me just give you a brief flow chart of how this simple algorithm operates. Okay, so we start the simulation here, then we take a initial guess values of u star, v star, w star and p star. Okay, then what we will do, we will use these values to get a temporary value for the u and p. Okay, so what we will solve? We will solve the discretized momentum equation, okay, which is nothing but ap up star equal to a and b u and b star plus gradient of p star plus b. Okay, and also ap vp star equal to a and b v and b star plus gradient is I cap, this will be j cap, gradient of p star plus b. Okay, let's write it as v u or something like that, u. Okay, up to this part it is clear. So we start our simulation. So at the beginning we take some guess values for all the unknown quantities, that is the u, v and w. We take the values of u star, v star, w star and p star. Then we use these values and plug them in the momentum equation, the discretized momentum equation, and once we have the discretized momentum equation solved, then we will have some new guess values of u star, v star and w star, right? Now once we have these values, we can again solve what? The pressure correction equation. A and B, P and B prime plus some function of u star, v star and w star. Okay, this part is clear. Solve the now we solve the pressure correction equation, okay, using the gas values. And after solving so the gas values here, so one thing to note is that the gas values here does not satisfy momentum and mass conservation, because these are just random guesses, right? These values do not satisfy momentum and mass conservation. But once we have solved this momentum equation, now these values, they satisfy momentum conservation but does not satisfy continuity. Okay, now it satisfies momentum equation but does not satisfy the continuity equation. So to satisfy the continuity equation, what do we need to do? Now that we have the pressure correction terms, right? Now that we have the pressure correction term, we use them to correct pressure and velocity, right? We use them to correct the pressure and velocity. So the new P, let's write it as P star plus P prime, and also U will be something like U star plus D times P I minus 1 minus I, right? This is the U prime part, if you remember. And similarly for V also, P prime J minus 1 minus P J, something like that. Okay, so now that we have the new values P, U and V, these satisfy the okay. Right now it got right now it got deleted, or for some time it was like this only? Is it visible now? Is it visible now? What about now? Is it visible now? I have shared the screen from my end. Okay. Okay, so yeah, so after that we have the pressure correction term. We correct the pressures and the velocities using the pressure corrections. Now that we have the new values, they satisfy the continuity but not the momentum conservation. Okay, now we have now that we have the updated values, what will we do is that we will take these values as the new guess values. Okay, we will take these values as the new guess values, and again do the same step that we have done from the start. Okay, we again do the same step and we continue it until we see that the U, V and pressure are not changing from time to time. Okay, from each iteration to not time to time, after each iteration, if the value of U, V and pressure is not changing significantly, then we know that the solution has converged. Okay, so any problem till now? I will again give a brief overview of the whole algorithm. If any issue, you can unmute yourself and ask me. Okay, so let me just give you a brief overview again, then we will stop the today's tutorial class. Okay, so we start the simulation, we have our boundary values, we have our initial conditions and everything. So initially what we will do is we will take a guess value. We will take a guess value of all the variables, unknown variables that we require to find. Okay, so once that we have these guess values, we will plug them in the momentum conservation equation, and now that we have the discretized momentum conservation equation with the guess values, we will be able to compute a better guess value which satisfies the momentum equation. So after solving the momentum equation, we get the new guess values and we use it again to solve the pressure correction equation. Once we have the pressure correction equation, we have our pressure correction term. With this pressure correction term, we correct our velocities and pressure fields using these relations. And once all of this is done, we check whether the values that we have right now, how much it differs from the value that we started. If it is varying quite significantly, we will again take the values that we obtain after this whole step and use it as an initial guess for the whole algorithm. Then we will again do the same thing using the guess values, solve the momentum conservation, and using the momentum conservation equation solved values, we solve for the pressure correction. For the with the pressure correction term, we correct the pressures and velocity fields, and then we have finally have the value. Then we again check it whether it is whether it has converged or not, whether the difference between the two values are below the tolerance limit. And once that is done, once the tolerance once the difference between the error has the error between the two consecutive iteration field values have gone below the tolerance level, then we have finally arrived at the converged solution. Okay, so this is the whole step. I will recommend you to derive it yourself so that you have much more clarity. Okay, so it's already time. I think we can stop for now. Any questions, any queries? Okay, seems not. Okay then, thank you guys. I'll meet you in the next tutorial. Thank you, Devraj. Good night.